So this is summarized in the word integration of the constitutive equation. In general, we will see that what we obtain as what we call a material model or constitutive model finally comes in the form of a partial, an ordinary differential equation, in which we can summarize as this one, in which there is a certain variable, for instance, the stresses, that depends on a certain parameter, time, for instance, the parameter with respect to which we want to integrate, and also on the derivative of that. And this is an equation that is zero. We will have generally an initial condition that's saying what is the value of this equation at the initial time. From now on, we'll assume that the initial time is t equal to 0, and then we'll know that. And from that, we would like to integrate that and obtain how is the value of x for any t as a certain function of time. That's the goal of any integration of an ordinary differential equation of first order. Of course, we can extend that to higher orders too. Well, sometimes this can be integrated analytically using these tricks or these methods that we know in any course on differential equations. We can obtain this function. I anticipate that this is completely uncommon in our case. So there is no easy way or trivial way for the general case to integrate that equation such that for every time we know the stresses of at the material point that we are examining. So in general, we have to resort to what is called the numerical integration. Numerical integration, in which what we do is just we split the time interval of interest. So we're starting at time t equals 0 and ending at time capital T. And then we split that in a number of time intervals. And in general, in such a way that these intervals can have the same width, say delta t, as the difference of t at time ti plus 1 minus t time ti, or can even be variable time step. That's not a relevant issue. Every of these intervals, the closed interval ti plus 1, is what we call the time interval or time step I plus 1. So we attach this time interval to the end of the bounds of the interval. These time intervals are disjoints, and the sum, the set sum of the union of all these intervals is the complete time of interest. And then we just are somehow satisfied with knowing not the value of the function at all times, but only at these discrete times in which we have split the interval of interest. It is well known that at the more times we have here, the more we converge, the more we approach the theoretical analytical solution. That's what we call convergence or consistency. Okay. So this will be our goal. We know that we can commit an error in general, which is associated to the length delta t, but we also know that the smaller is delta t, the smaller is this error. Of course, that there are procedures that for the same delta t produce smaller error than others. So that's something that you are going to examine too. For given discretization in time, what is the best method qualified as that produces smaller errors? There are methods that produce larger errors than others. But we will always have, in general, a except in very few cases, we always have an error associated to that. Okay. Okay. So let's apply these concepts to the constitutive model that we have examined. Let me recall that the only partial differential equation that appeared in the model is that said that the evolution of R is equal to lambda. This lambda being given by the so-called Karush-Tucker conditions, loading and unloading. I recall that in terms that at any time t, lambda has to be greater or equal to 0. G, which is the function that indicates that determines the elastic domain, G has to be smaller or equal than 0, and the product lambda times G has to be always equal to 0. And the persistency condition says that as G is equal to 0, then lambda G dot standing for the differentiation with respect to time, the evolution, has to be equal to 0. Okay? And then according to that, during the last lecture, we examined the implications of that in terms of defining 3 different states, what we call the elastic state, the inelastic or damaged state. In that, we also define something that could be termed a loading, or neutral loading, and pure loading. Okay, let's review all that. We expect that this implicitly provides, through time integration with the appropriate definition of G being the norm of the strains at every time t, minus the value of R, which is what we want to compute at this time t, which is always smaller and equal than 0, according to that. We want to integrate this time differential equation. You see the time derivative dot appears here. And we want to integrate that, providing at the time t, the current value of R in terms of strains at previous times. So, as I said, we want that at certain time ti, we want to know the value of the variable that we want to integrate, in that case is R, in terms of the data, the strains, at, or whatever is the data, at previous time steps. So that is a time advancing algorithm, which is the way that all the numerical integration of algorithms for time work. Okay. So now let's examine what we had from the definition of the model. We defined the elastic state when the point was inside the elastic domain. Since the elastic domain was defined in the strain space by this function tau, the norm, minus R being equal to 0, belonging to the interior of that means that this is strictly minor than 0. So that means that the norm is smaller than R at this time. And we saw, I'm not going to prove, but in view of that, we saw that as a consequence of that, I can just recall that this was because since this is then different from 0, this implies that lambda is equal to 0 in this condition. So if lambda is equal to 0, that implies that R dot is equal to 0. There is no evolution of R, and that's the situation. The situation is clearly that R dot is equal to 0. There is no evolution of R. Tau epsilon is smaller than R. And nothing is said about tau dot epsilon, the evolution of tau dot, which can be positive or negative. Okay? That is the situation in this case. Then we also had what we call the inelastic damage state, in which the point that the strain at the strain space were just on the limit, on the surface of the elastic domain, what we call, do you remember the name? The boundary of the elastic domain, we call damage surface, okay? So this was characterized by G being equal to 0, that meaning that in this case, tau epsilon is strictly equal to R. The norm is equal to R, by definition of what is an elastic state. And then here we could distinguish two different situations. One is that G dot is smaller than 0. G dot smaller than 0 means that tau dot minus R dot is smaller than 0. This is what we call unloading, so the point being on the damaged surface moves towards the interior. And this was, again, by reasoning on the Karish-Tucker conditions, this implied that lambda also took the value 0, which is compatible at strictly equal to 0. So the evolution equation for the internal variables said that there is no evolution of R. R dot equals 0. So this case is characterized by R dot equal to 0. And of course, if R dot is equal to 0, then this equation, this being equal to 0, this equation states that tau dot has to be smaller than 0. The norm, the rate of the norm has to be smaller than 0. Okay? So that's the case in which the point moves, staying on the surface, on the damaged surface, moves towards the interior, decreases the norm, so approaches or diminishes the distance to the origin, so moves towards the interior of the elastic domain. Then there was another alternative, this being strictly equal to 0. This being strictly equal to 0, that means that tau dot minus R dot is equal to 0. And here, nothing is in principle defined about lambda, because being G dot equal to 0, lambda can be either greater or equal to 0. And this gave rise to two different situations, one that we call neutral loading, in which lambda was equal to 0. Again, if lambda is equal to 0, then R dot is equal to 0, and they were called neutral loading, and that was the case in which the point was on the damaged surface and moved on the damaged surface. So the damaged surface didn't evolve, but the point was damaged and remained damaged in the damaged surface. But in that case, this equation said that since R dot is equal to 0 and this is equal to 0, then tau epsilon is equal to 0. So that case is characterized by tau epsilon equal R, R dot equals 0, and tau dot equals 0 too. The other alternative, what we term pure loading, in which the point staying on the damaged surface tend to move out towards outside of the damaged surface, and this was not permitted by this fact, and then the damaged surface grows, expanded, so as to contain the point in its motion towards the exterior. And this is characterized by G dot equal to 0, which means that tau epsilon equal R dot, but then lambda is greater than 0. So there is evolution of R dot, there is evolution, the surface moves, grows, and then this case is characterized by tau epsilon equal R, but R dot equal tau dot greater than 0. Okay? Okay. So this should be strictly greater than 0. Okay? This is a mistake. And there was no other possibility. For instance, the possibility G dot being greater than 0 is not possible. That would mean that in a subsequent time, the point that was on the damaged surface would stay outside the damaged surface at the subsequent time, and this was not possible. So this was all the possible panorama. Okay? So look, it's interesting to see that this is enough to determine the value of R. Don't forget that our goal is to determine at time t how much is RT, knowing the strains at the previous times, the history of the strains. That's our goal. And curiously enough, this is enough to do that. That is to integrate the evolution equation. Why? Look, from this sketch here, we can conclude the following about R. How much is the, imagine that we have here R and here the time. What is the initial value of R? We said always that the initial value of R is an initial threshold that we term R0. We'll see today what is this. This is a material property. We'll see how do we characterize this material property. Initially, R takes this value, R0. Okay? Okay. What is the initial value of the norm of the strains? Assuming that we start in the undeformed configuration, initially we don't have any strains. So we can consider always the body I have just have, excuse me, no strains. Then it would have some, but at the beginning there are no strains. So if there are no strains, the initial value of tau is the certain norm of epsilon as a property of any norm. The value of the norm for the argument being equal to 0 is equal to 0. So the point starts at the center of the initial position of the strains at the point is at the origin 0. Okay, that's what we know. Second thing, R never decreases. Look, is that true? Yes. Look, all the panorama is that. So R, according to that, R dot is equal to 0 here, R dot is equal to 0 here, R dot is equal to 0 here, and R dot is greater than 0 here. Never is smaller than 0. So R dot always increase, which is also comes from this equation, this lambda being greater than 0. Okay? So that is just comes from examination of this. Look, tau epsilon is always smaller or equal than R. Look, again, if we go back here, we see that in this situation, tau epsilon is smaller than R. Here, tau epsilon is equal to R. So only these two solutions. Never happens that tau epsilon is larger than R. So in other ways, if I plot the evolution of R along time, R, according to this, of tau, R, according to this, starts here, and tau starts here at 0. And then the blue line, that one plotting the evolution of tau, has to remain always below the red line, or the brown line, which is the one representing the evolution of R. That's what it says, that tau is always smaller than R. Okay? They are both positive, and this is always smaller than 1. Then, when tau, I said that tau is always smaller or equal. Okay? So, this comes from the fact that G, which is tau epsilon minus R, is smaller than 0. Okay? G is smaller than 0, so this means that tau is smaller or equal than R. For the cases in which this equality holds, tau epsilon equal R, then, which is this case here, tau epsilon equal R, then either R dot is equal to 0, okay? So that means that in that case, tau dot epsilon is smaller than 0. So when that is either smaller, and at the most, the increase, the value, the rate of increasing of tau is equal to R dot. Tau never increases faster than R dot. Okay? So how does it translate into this plot here? Well, it says that, okay, imagine that initial value of tau is R, of R is R0, tau starts here. I can have some evolution a long time, and while tau epsilon is smaller than R, there is no evolution of tau. Okay? But at the point that tau epsilon reaches the current value of R, then it could happen two things. If tau decreases, then R doesn't evolve. But if tau increases, tau and R grow together. So they take the same value. So that's what is said here. If tau grows, and tau equals r, then the evolution of tau is the same than r. Which is expected here in that when tau and epsilon are the same, have the same value, if tau grows, increases, then r increases in the same way. Exactly in the same way. Okay? But even when tau is equals to r, for this, in that point here, if tau epsilon decreases, then r becomes frozen. And then tau goes down, but r becomes frozen. R, I recall that r dot is always greater or equal than 0. So r dot can never do that like that. R dot can be do like that, last, increase, stop, increase, etc. Tau epsilon, that has no constraint. But from examination of these conditions, on the view of these conditions, on the light of these conditions, then we can see the evolution has to be something like that, in which r, the brown line, is always above the blue line. When one reaches to the other, if tau grows, r grows, so they evolve together, taking the same value. But as one decreases, as tau decreases, the other remains frozen. Okay? So the evolution has to be there. And this helps to say, well, on the light of this curve, are we able to say what is the value of epsilon given a certain t? And then, if I know t, I know tau epsilon at this time, and at all the previous times. Okay? Is that I'm able to say how much is r at this time? And I say, well, the answer is that. At the time t, r is the maximum, the historical maximum of all possible previous taus and r0. That's what is expressed here. For times s belonging to the interval 0, the current time, t is the current time, s then can be any previous time here. The maximum of the value of tau, so the blue line up to this point, including r0 as the maximum, is the current value of tau. Let's see how this holds, for instance. Imagine that t is here. T is in this range here. What would be the value of r? The maximum of r0 and all the previous taus, which are smaller than r0, so then, for this point, r is equal to r0. What happens if we are in a point like that? In a point like that, the value of r has to be compared with r0 or the historical maximum of tau in previous times, which is the present value of tau. So I have to choose the maximum of r0 or that current value. So it's tau at this time. What happens in a point like that? The value of r is the historical maximum of tau r0 or r0 at previous times. What is the maximum attained value of r at previous time? This one. So r remains that one. Okay? And when I arrive here, I'm in the situation in that both are equal. And tau epsilon grows, so r grows in the same way. And for instance, at this time here, how much would be r? The maximum of r0 or the maximum historical value, which is the current value. Okay? So now, if I done a time advancing algorithm, and I know the values of r and the values of epsilon, essentially the values of epsilon and r, at any of the previous time steps, then if I know these ones and I have them stored, then I should be able to determine r for any epsilon. If I now want to go to any other epsilon, whenever I have the record of the evolution of tau epsilon, by comparing that, I take the maximum of the previous times of tau and compare the maximum of that and take the maximum of both, the history and this one, and this is the current value of R. So that is a very specific case, because this is the exact solution. There is no integration error in that case. There is no integration error. So given a certain history of the strains, I can determine the current value of the R at time t. Given the history of the strains and then of the norm tau at the previous times, then I can determine R. And that's it. So what I would have to do in that case, we'll see that we can evolve like that. But in principle, just store the value of tau, the maximum value of tau, along the time advancing process, and then compare this value with R0 on that. And that is the value of R. That's it. Okay? This stored value can be R0 here. It's changing at every time here. The stored value keeps frozen here. The stored value increases here, and so on. I just have to keep one in memory, one value in memory. Okay? Well, that means, any questions so far? It's clear? It's clear?
But you can have an error if you don't have enough time steps?
No,
for
because...
If you start just for a time step before the first one, in which you have the R0, and then you want to find...
Yes, I mean, yes, I could have, I mean, yes, that's right. There's a certain error, but this error, yeah, you are right. Somehow the error depends on the information I have. But I mean, if I have the information, I don't commit no error due to the integration. Okay, that's the maybe a subtle additional explanation of that. Look, then what does that mean? That for every time, if I know the strains and the history, I am able to determine the norm. Knowing the norm, I can determine R as the historical maximum. If I am able to determine R, I can determine the value, what we call the hardening softening variable Q, which is an explicit function of R. We'll go back to that. If I know Q and R at time t, I can compute the damage variable at this time t as 1 minus Qt over RT. And from that, I can just compute the stresses at this time t in terms of the strains at this time t, which are supposed known, and then the value dt that I've just computed, and C being the elastic material property tensor. And that's it. That's integration.